Hello and welcome to this calculus video. Today we'll be talking about curve sketching.
Math 112.
The internet is pretty good at sketching curves. I use Desmos for all the graphs in these videos, but a computer-generated graph has limitations. For instance, it might be hard to see exactly where the local extrema of a curve are. Using everything we have learned so far involving limits and the derivative, we can produce accurate sketches as well as knowing exactly what and where important features occur. Our textbook outlines a procedure to find the important features of a function ready for sketching. We will illustrate this process with the example f of x equals 2x squared divided by x squared minus 1. Firstly, we find the domain of the function, any intercepts, and any asymptotes. As our function is rational, we can find its domain by looking at the zeros of the denominator. In this case, that is x equals plus minus 1. So the domain is all reals except 1 and minus 1. We find the y-intercept by plugging in x equals 0, and we get y equals 0. To find the x-intercepts, we solve the equation f of x equals 0, which has only one solution, x equals 0. The horizontal asymptotes of a rational function are also straightforward. We know from lim 3 that the horizontal asymptotes of f of x are y equals 2, because the top and bottom of f are quadratics and the quotient of the leading terms is 2. As for vertical asymptotes, we know they occur at x equals 1 and x equals minus 1, but we also want to know what kind they are. To do this, we have to look at the left and right limits of f of x at plus minus 1. We note that if x is greater than 1 or less than minus 1, then f of x is positive, while if x is between plus minus 1, then f of x is negative. Therefore, the limits from the outside are plus infinity, while from the inside they are negative infinity. Now we start gathering information from the derivative. We want to find the intervals of increase or decrease of f and all the local extrema. To do this, we draw a sign chart for the derivative. In our example, we can compute f prime of x to be negative 4x over x squared minus 1 squared. Since the denominator is a square, the sign of f prime of x is controlled by the numerator, so it is positive when x is negative and negative when x is positive, with a critical number at x equals 0. The first derivative test tells us this is a local maximum. Now we use the second derivative to determine concavity. The second derivative of f of x is f double prime of x equals 12x squared plus 4 all over x squared minus 1 cubed. Since the numerator is greater than 0, we know that the sign is controlled by the denominator. So the second derivative is negative when x is between plus minus 1, and it is positive otherwise. Now we put this all together. We start by adding dashed lines for the asymptotes and marking the intercepts and any local extrema or critical points. We then join up these points respecting the concavity, increasing/decreasing, and limit behavior we found before. This is just one example, and a different example could go very differently. The strategy we outline above is a good starting point, but you could do things in a different order and still form a reasonable sketch. That's all for now, folks. Today we talked about sketching a graph. We combined all the tools we've developed so far to produce accurate sketches of curves by finding intercepts, asymptotes, extrema, intervals of increase and decrease, and concavity of a function.